This is Saxon's Trig Lesson 5, Exponents and Radicals, Complex Numbers, Areas of Similar Geometric Figures, and Diagonals of Rectangular Solids are all in this lesson. So starting with Section A, Exponents and Radicals, we've talked briefly a little bit before in the earlier lessons about these exponents. However, I tend to discover that students coming in have not mastered this. So if you are having trouble here, make sure that you get this down because we do a lot of these within this book. So let's jump straight into example 1, where it asks us to simplify a root that has x cubed and y in it, and then a fourth root because it has the little 4 there with an x, y cubed in it. So what we first want to do is change all of these over to exponents that we can then combine together, because these are not like term pieces. I can't really multiply them. They're all over the place. This is a square root. This is a fourth root. So I just can't do anything other than change them over to exponents. So this x has an exponent of a 3. That is the numerator of its exponent. Its denominator comes from its root number. So I keep saying square root when I say it. What number is implied with a square root? That is the number 2. So this is x to the 3 halves. This is y, an implied exponent of 1, same root of 2. Now continuing, this one is an x, implied exponent of 1, denominator of a 4, x to the 1/4. This one is y, exponent of 3, root number of 4 for the denominator. Now I have them in a way that a format that I can then multiply. So these have the x bases. When you multiply bases, you add exponents. That is a rule that you definitely should have learned in algebra. So I'm basically trying to do 3 halves plus 1/4. And the same with my y's, 1/2 plus 3/4. And now I need common denominators to add those together. So this should be a common denominator of 4. And that's going to change this to a 6 to keep it in balance. And this one's already in 4, so now I add 6/4 plus 1/4, so x to the 7/4. Same thing over here, denominator of 4. This one changes to a 4, this one a 2. 2 plus 3 is 5/4. And I can leave them improper, and that's the answer for example 1. Example 2 gives us a to the x over 2, then a parenthesis y with 2 minus x, exponent of 1/2, over top of a to the 3x, y to the negative 2x. I know I need to put all of my a terms together and my y terms together. So the a's are already in a simple enough format that I can combine them. This y, this one, and the top is a little more messy. So again, in these type of problems, you can choose whichever method you desire to start with. The specific order in which you solve things does not matter. So just to write it in simplified form, I'm going to change this a to x over 2, and I'm going to choose to move this one up to this one to join it. Now, I do know, I'm pretty sure it's going to make a negative, and then I'll have to fix it, but for right now, I'm just going to do it that way. So when I move it up, whenever I change the location of a base, I change the sign of its exponent. Since this one is positive, it's going to go to a minus. And rather than writing another a to the minus 3x, I know that when I have two a bases, they're multiplying together. Therefore, I'm adding them together. Multiplying bases add exponents. So I'm just going to write that this is a minus 3x, so I have it in one a term. Now it's all combined. Okay, this y has an exponent of 2 minus x and another exponent of 1/2. I can't work with it this way. I want them to be all together with one y base, not this mess. So remember the rule. When I have a base with two exponents, I multiply. So let me go back and clarify again. When I'm dealing with two different bases, I am adding or subtracting those exponents together. Basically add, just depends on the sign. When I have one base with two sets of exponents, I want to multiply. So this is a distribute situation. 1/2 times 2 is 1 minus 1/2 times x is a half x, or that can be written as x over 2, same thing either way. I also want to move this y up to join the top, so I'm going to change the sign when I bring it up and make it plus 2x in combination already so that I'm ready to simplify. This needs a common denominator to put it together, which would be a 2, which is changing this to a 6. So a 1x minus 6x is negative 5x. I said I thought it would come out negative over 2. And then the y needs a common denominator of 2 to combine everything. So this changes to 2, this changes to 2. This gets a 2, this changes it to a 4. So now this 2 over 2, I actually didn't need to change it because it doesn't have an x, so I could have left it 1. It kind of really doesn't matter. So we have 1, and then negative 1x implied plus 4x. So negative 1x plus 4x is positive 3x over 2. Now, did the book leave theirs? They did leave it with a negative. So they left it with everything in the numerator. Typically, math answers tend to not want exponents in negative, and so this would shove back down, but a fraction, or this thing over another, making it a fraction, is a little more complicated looking, so they leave it here. Whichever format you choose to put it in is going to be fine. All right, example 3 has x to the negative 2 plus y to the negative 2 over parenthesis x, y, and an exponent of negative 1. Okay, this tends to throw students. This plus sign here in between these statements. Can you move this down and make it a positive and this down and make it a positive and bring that plus with it? No, you cannot. Because this is an addition term, these things are stuck together as a plus. If they were multiplying, I can bring things down separately. But when they're plus, anytime you see a plus or a minus in between terms, you have to picture that as a parenthesis stuck together. It can't be separated. So you can change this one over to not be negative here in the numerator. So instead of having it x to the negative 2, I'm going to write that as x. I want to flip it. So, oh, sorry, that's backwards. X over 1 is implied here, so this should be 1 over x when you flip it, and now its exponent is positive. Plus, same thing happening here. This is implying y over 1, flip it so it's no longer negative, and it's 1 over y squared. Okay. All over top of, and this is one base with a 1 for an exponent and a second base of this negative 1. One base, two exponents, I multiply. So this gets x to the negative 1. Same identical thing happening with the y, so it's y to the negative 1. Or you can just picture this negative 1 as distributing to both. However your brain wants to do it is fine. In order to combine these together, they must have like terms. They must be like terms, so I need the same base. That means x squared, y squared is the combined base. So what does this denominator need to be this? It has the x squared, it needs the y squared. So we're going to change this numerator to y squared. Now repeat, this base needs to match this base. It has the y, it needs the x. So this gets the x squared to keep it in balance for the numerator. Now I have y squared plus x squared all over this stuff. Okay. So again, I can change these so that they're not in their negative format, which would mean all of this is over top of 1 over x multiplying with 1 over y. So I'm just going to write this as one fraction 1 over xy. I have a fraction over a fraction. That means division because fractions mean to divide. When I divide a fraction, I actually flip it and change it to multiply. So this y squared plus x squared over x squared y squared is multiplying with, flip the bottom one, making it x y over 1. So the 1 doesn't really matter, but I'm going to keep it there as a placeholder. Now, I can't do anything with this because it is a positive. It's stuck in a parenthesis. It is a unit unto itself. I can't cancel it. I can't change it. However, this xy is in the numerator and this stuff is in the denominator, and they're all multiplying, so they're fair game for canceling. So 1x up here will cancel 1x down here and leave that a 1. Same thing with this y. It's going to cancel this one down to a 1. So what do I have at the end? Y squared plus x squared over top of x y. And again, the book, they probably did it in a different order than I did, but you still get the same answer. Kind of out of, well, I'll just box this. That is the final answer. You don't need the parenthesis in it. Example 4 on page 44 begins with 3, an exponent of 3 halves, minus 4, exponent root 2 thirds, plus 2 square root of 24. In order to work this problem, I need some like terms, and I don't have any. They're all different. So let me see if I can manipulate and change things and turn them into something that is the same. This can be written as a separated root 3 and root 2. This one can be written as a separated root 2, root 3. I'm leaving some space for a reason, plus 2, and then this 24 is going to do that same split, so I see how it simplifies. So let's try 2 and 12, 2 and 6, 2 and 3. I have a set of 2's, so that's going to pull out and put another 2 with this. There's no mates for 2 and 3, so they multiply back together and make root 6. Now I left the spaces here because I know my next job is to fix this radical in the denominator. And to do that, I multiply by a root 2 because root 2 times root 2 is 2. Square root of 4 is 2. If I do that on the bottom, I must do the same thing on the top or my problem is no longer in balance. Same thing here, root 3, root 3. So this has become 3 radical 6, if I put 2 and 3 together, over 2 minus 4 root 6 over 3 plus 4 root 6. Now I've simplified that as far as I can. I can, however, give all of these a common denominator, and I do see that they now all are like terms with root 6's. My common denominator between 2 and 3 will be 6. So if I turn this into a 6, I've multiplied it by 3, which makes this a 9. Turn this one into 6 by multiplying by 2, that makes that 8. This didn't have a denominator, implying a 1, so if I put a 6 here, 6 times 4, 24. Now 9 minus 8 is 1. 1 plus 24 is 25 root 6 over 6. And if at that point I could reduce these outer numbers only, I would do that. This is a root 6. You don't reduce it with a number that's not also in a root. So that is the final answer for example 4. Example 5. Root 2 plus root x is multiplying with 1 minus root x. So this needs to distribute, or if you prefer, FOIL, just depending on how you're used to thinking your way through it. I tend to use the mathematical term distribute more than I use FOIL, but I think it was drilled into you in Algebra 2 about FOIL. But you're going to take this root 2 and multiply it with this one, and then with this one, and then the root x with both of those parts. So root 2 times 1 is root 2. Root 2 times root x is multiplying within, and because that's a minus, I'll write a minus, the square root of, and they multiply together, 2x, plus root x times 1, root x, and then root x times root x, plus and minus is a minus. And root x times root x is basically root x squared, and a root and a squared cancel each other off, and you're just left with the inside content of x. Are any of these like terms? Do they share the same thing inside? No, they're all different. So I cannot combine anything, and that becomes the final answer as far as I can take it. The book rearranges it to a weird format. I would rather see it this way, and I don't think the answer keys tend to separate them, but for some reason in this example it shows you that you can factor out the root x from these two terms, but I find that's just to be a lot more confusing. All right, part B is complex numbers. So regular numbers that we've been working with, 2s, 4, 5, a billion, whatever, we recognize. Square roots of things we recognize as basically normal. However, when we get to a term that is an I, it implies imaginary numbers. So mathematicians in the past basically discovered that they could manipulate numbers and end up with a negative inside a square root, implying a -1. When that happened, they could use math rules that seemed to work, but they couldn't make real-world applications with a negative inside a square root. So because it became a math concept and not a real-world kind of application, they decided to call them imaginary numbers. They don't exist in the ability to use them in the real world, but they exist mathematically here on the paper, and I can manipulate them. So I basically means the square root of -1. And those are now called complex if it has an I in it. All right, at this point, I'm going to stop and give you the I chart because I find that most students just don't know it, and you will definitely want it in your notes to keep. So we've identified I as the start at square root of -1. So what happens when I square that? Well, if I multiply the square root of -1 times the square root of -1, the square roots kill each other off in being squared, and I just keep the inside contents of -1. If I cube it, I take the last one that I had and I'm adding another I to it. So it's basically -I, -1I, same thing. I to the fourth means -1I times -1I. -1 times -1 goes to positive. I times I is I squared. Oh, what was I squared? Oh, it was the -1. So there's that. Just a second, I feel like I have, no, I wrote that, just a second. -1 times +1. This should be +1. I didn't think that felt right. And then I to the fifth adds another I to that, which makes it 1I. And then at I to the sixth, you're repeating the same as I squared, which is -1. And then I to the seventh would match with I cubed, and so on and so on and so on. So here is your I chart for use in solving these problems. Okay, in example 6, we have 3I cubed plus 2I to the fifth minus 3I plus 2I squared. And I'm going to use my I chart to simplify. 3I cubed is -I, so this becomes -3I. I to the fifth is I, so plus 2I, minus 3i, no change. I never want to put it into a root format. I want to leave it in i's as I have the rest of my problem doing. I squared is -1. -1 times 2 makes -2. That one doesn't have an I. So now I combine my like terms, which are all the ones with i's, and that gives me -3 plus 2 is -1. -1 minus 3 more is -4i minus 2. In the book, they put the I term as last, so they would write it as -2 minus 4i. Either way is okay. I'm going to leave mine this way. Just note that typically the I does tend to be written at the end in mathematics. Example 7. We have square root of -3, square root of 4, plus 3 square root of -2, square root of -9, plus square root of -16, plus square root of 16. So every time I spot a negative inside a square root, I immediately know that I am pulling that out as an I and then leaving the number as a positive. The square root of 4 is 2. I'm going to put a parenthesis around that just to remind me that they're multiplying, plus 3i root 2, I square root of 9, I'm going to go ahead and write that as 3, and I'm going to come back and multiply all those together, plus I square root of 16 is 4. Now technically that should be written as 4i, just so I match the right format. I'll fix it in my next step, plus square root of 16 is 4. So now this becomes 2i root 3 because I want my number in front, then my I ending with my radical, plus 3 times 3 is 9, I times I is I squared, ending with the root 2, plus, and I said I'd fix that, 4i plus 4. Do I have any matches to root 3? No, so this guy stays the same. However, this I squared is really -1, so -1 times this 9 makes this -9. Root 2, carrying with. All right, do I have anything that has an I term plain? This one has an I, but it has a root 3, so no match. So basically, these 4 pieces would be what I would box as my answer. Now again, in the book, they take the 2 I terms and separate the I out, but I would not recommend doing that. I would just leave it in those 4 pieces.